Hi everybody. Today we want to speak about the properties of a porous material, which we have analyzed with optiSLang and GeoDict. And to give you an idea of what we will present you, we have created the outline as follows. At first we want to start to present optiSLang and GeoDict a little bit, and then we want to go into the details of the simulation model and the optimization task. And then we want to check the process integration and the design of experiment, as well as the sensitivity analysis. And then we want to go on with the optimization and a little summary. So first of all, this little look into optiSLang. optiSLang is made for real-world computer-aided engineering applications. So I guess everybody of you knows some of these applications, from a car crash to a bridge to an airplane. And so I guess now it's a little bit more obvious what I'm showing. And so optiSLang is at the end easy and safe to use, because we want to offer you predefined workflows, and how these look like you will see in the second part of the webinar when we make a little live example. As well, we are offering algorithmic wizards, so we will see a lot of different traffic lights which will indicate you which algorithm you should use for your special application, and which algorithms is optiSLang offering. It's at first algorithms for the process automation, because we want to do a parameter study, and these studies contains a lot of different simulations, and these should be done automatically. These parameter studies are made for design variation, so we want to change a geometry or a filter size and stuff like that to check out which would be a very good set of parameters. And to find these good set of parameters, we would start with a sensitivity analysis always to identify the important parameters, and then we would go on with an optimization study to identify these improvement we can make when we choose a specific set of parameters. And then we go on, or we could go on with a robustness evaluation and a reliability analysis, but in this webinar we will stick to sensitivity analysis and optimization. So how does such a workflow look like? We have optiSLang here in the middle of the workflow. So optiSLang is for the workflow management, and it can communicate with a lot of different numerical solvers. Today we want to show you GeoDict. And what is optiSLang doing with these GeoDict simulations? We have input parameters, and we change them, varying them to change the simulation at the end, to find a set of output parameters, to find the surrogate, or to find a surrogate model between them. That's the model which describes how the output behaves in the case that one specific input is changed. And how this is done in detail, I will show later on, after Aaron has shown how GeoDict is working and what's the task for today.
Thank you. Now I give you a little overview over our company. We are the Map to Market GmbH. We create software to analyze the design and porous composite materials. Our software is called GeoDict. You can import real data, your real life problem, using image giving materials, for example, MuCD or FIBSEM-based data, and import them into GeoDict. We are spun off from the Fraunhofer Institute. We are based in Kaiserslautern. We have more than 150 clients worldwide. As said, we are spun off from the Fraunhofer. So, and we closely cooperate with them, so our solvers are scientifically proven. We not only provide our software, but we also offer trainings, projects, and support. So you are not on your own if you want to use GeoDict. So what's this so-called GeoDict do? We do go into filtration, into electrochemistry, composites, and oil and gas. Yeah, you can analyze your structure as seen in various ways. For filtration, you can have a look on fiber structures or grain structures. For electrochemistry, you can look at cathodes or electrodes. Composites, you have various multi-layer composites you can analyze, and digital rock physics, you can have a look on your rocks or various others, sand control screens, for example. And what would a typical GeoDict workflow look like? You import your real-life data and then analyze the materials. If you import your real-life data, you don't know any analytic data of them. So you are not knowing the fiber diameter, the pore size distribution, or such things. But you can use GeoDict to analyze your material and get those data, and then model your material, and then use the modeled material to calculate, for example, Stokes flow through it, to know your permeability or how the flow field would look like. And if the if your material has not the desired properties, you can start varying the input parameters and optimize your material with respect to lower permeability, for example. And in that optimization process, optiSLang can be used, but it can also be used in other ways, for example, robustness evaluation. And if you have your optimized material, you can export it. For example, we offer STL export or such things. So if you want to characterize your material, we have a wide range. Those are only a few examples. For example, you can look for the fiber orientation, fiber diameter. You can look for the largest through pore. What's the largest pore going through your material? And many more. And also the properties, as I said, permeability. You can look for the flow field. You can do filtration analysis. And you can also look at conductivity, electrical and thermal, and again, various other. So you have a large tools you can use. And if we now have a look at what GeoDict looks like, that is not an imported structure, that's a structure directly generated with GeoDict. We also offer structure generators. So we would, for example, just go into edit, fiber options. We can choose the diameter, the orientations, and then it generates, and GeoDict generates us our structure. And with this structure, it should be the same as before. With this structure, in this case a fiber structure, we can do a filter simulation run. You see the fiber generator is really fast, like all our generators. And with that, we can, for example, start a filtration simulation. What does happen in a filtration simulation? First, we have a look at the results. Therefore, I load the particles. In a filtration simulation, we give in the inflow plane a defined number of particles and use the flow field we calculate to simulate how the particles behave in the structure and see how many are filtered, what's the pressure drop, what's the dust holding capacity. And we do that several number of times. In this example, 30 times, and see what's the overall pressure drop in the end and how does it perform over the different batches. So we see in batch 1, very much particles reach the bottom, are not filtered. And if we jump to a later batch, we see how the structure is filling with the particle. We see it also better if we disable the structure and see, yeah, we can very nicely see how the particles travel through the structure, even if we turn the velocity lower. And in the end, we can then have a look at this structure, see how the dust is distributed, and use the result file and can see, we also have a report, what's the filter efficiency per batch, what's the pressure drop per batch, and the deposited dust. And we also offer plots. Here the pressure drop is plotted and the dust holding capacity is plotted. But we also offer a Python interface. You can use the Python macro, you can record the Python macro of everything you are doing and then execute it again with different parameters. And you can also use Python to post-process the results. So you don't have to rely only on those results, but you can extract them with Python and create your own graphs if you need other graphs, for example. And yeah, this is the structure you have seen before. This is our starting structure. This structure you want to optimize. You see the parameters here. I showed you where you can enter them. And then I generated the structure and we want to vary those parameters and optimize for initial filter efficiency, initial and last pressure drop, and the dust holding capacity. And what do the results look like? In this case, we got that output with those parameters. I'm not going to read them because I'm not sure how much efficient that would be. But interesting is the optimization result. We could almost get 100% filter efficiency. The initial pressure drop got a little worse, but that's some kind of natural because if the efficiency goes up, the pressure goes up, also the pressure drop goes up. So optiSLang uses its mathematical knowledge to get a better, a good ratio between filter efficiency, initial and last pressure drop. And also we managed to increase the dust holding capacity. Yeah, I also compared both structures, to the left the original and to the right the optimized. We see the optimized has very little deposited dust at the bottom. But if we use, for example, various filter layers with a gradient, which both GeoDict and optiSLang can do, we also can get a better initial and last pressure drop and optimize the fiber structure even more. And last few graphs, the original structure is red. We see the pressure drop is slightly better than the optimized, higher than the optimized structure. And here for the optimized structure, we have more deposited dust. Yes. That are the results, so you don't get bored if we now show you how you can achieve those results.
Yeah, thanks Aaron for this presentation. And in the next minutes we will have a look on the generation, on the process integration, and on the result extraction within optiSLang, so you can get an idea on how we get these optimized results. So we want to go on with the process integration. And first of all, what's the idea of that process integration? We have a CAE process, this computer-aided engineering process with GeoDict. And now we say, okay, this process is a white box for optiSLang because you as engineer understands completely what GeoDict is doing here. And you have this simulation in control. And optiSLang is only changing design variables or scattering variables within this process to extract response variables. So design variables are the entities that define your design space where you can change the filter, and scattering variables would be variables which are influenced by production or random effects. So you can use a lot of different solvers within optiSLang, and you can couple them together, so you can define different workflows, and this is the workflow for GeoDict. First of all, we have this GeoDict Python script here. This is our input file because these files is defining what GeoDict should do, and so we can change parameters within these scripts, and then we can solve these GeoDict simulation, and then we can extract the results from the GeoDict files. So here you can see a view of these two files. And when we are able to integrate these files into the process, then we can go on and start with a design understanding. So this is the first part we want to do. So we want to investigate which parameters influencing the design we are looking at, so which are the important ones, and then we want to generate the best possible meta model or surrogate model. So within the sensitivity analysis, we go to Latin hypercube sampling. That's where we start. Here we want to sample within the design space you have defined with these parameters. Then we want to go on and generate this meta model of optimal prognosis. And with this meta model, we can determine which parameters are important to describe the behavior of your output variable. So this is one purpose of this meta model. The other purpose is that you can directly understand and reduce the optimization task, so you can see the behavior of these response within such a 3D plot or within other plots. And so you can decide, okay, I want to achieve a high filter efficiency. So you can directly decide, maybe I should increase the parameter ranges or something similar. And you can check for solver and extraction noise if this may occur. So in our special case, the workflow looks like that. First of all, we create a design of experiment with 50 designs, and these 50 designs will be solved by GeoDict, and from this solving process we get responses back, and with these responses we can calculate these meta models, and these meta models help us to evaluate the sensitivity and to find the important parameters. So how does it look in real? So this is a first glimpse of optiSLang, and when you want to integrate your solver, you have to use the solver wizard. Then in this case you have to choose GeoDict. Now we have to select the file we want to use for this simulation. So we have to choose the GeoPython file here. And when you have done that, the workflow is automatically generated. So you can directly see the workflow here. And now we can go on and select the parameters we want to use within the simulation. So we select our input parameters here, and these are within the setup here. So first of all, we need the standard deviation. And as well, we need the diameter for the fibers and the anisotropy. So now we have selected these important parameters, And as well, we should choose the parameters we want to use for the generation of the surrogate model. So in our presentations you have seen we have to use a pressure drop, we have to use the efficiency, and we need as well the particle load. No. Yeah. Total deposited dust. And we need the last pressure drop as well. So now we have set up the parametric solver system, and this is the first step for us to start with the sensitivity study, and this can be easily done when we take the sensitivity wizard and drag it on the parametric solver system. So here we have these parameters we initially defined within the parametric solver system, and now we can import from a file these parameter ranges, so we don't have to type them in manually. Now we only want to do a sensitivity study, so we can leave these criteria as empty, and then we are asked about the sampling method. So here you can see the first time this traffic light system, and the green traffic lights indicating, okay, you should use this method. For our purpose now, we want to choose other and to do only 50 simulations. And when we have done that, the sensitivity workflow is generated, and now we could easily set up the simulations to run only with a press on this play button here. And we want to go back to the slides at first. So here you can see the parameters and their ranges, and then we do these 50 simulations and get the results of this meta model of optimal prognosis. And yeah, here you can see the surrogate model for the efficiency, but we want to look a little bit more into detail onto that. So for that we say MOP show post-processing, and then we get the post-processing for that simulation here. And now we can, for example, have a look on the efficiency here, or we look onto the approximation of the initial pressure drop, and you can see that we can explain almost every of these responses very well. The total pressure drop, which is the difference between the last and the initial pressure drop, cannot be explained that good, but in this example we don't need that variable, so we can go on and can stick with these values. And when we want to go on, we want to go to the optimization. So the optimization is the, we should check the theory a little bit. Within the optimization, we want to find the parameter set which improves our performance compared to the initial design. And to do that, we start with using only the important parameters which we have found within the sensitivity study. So you have seen that within the sensitivity study, the diameter of the fibers was very, very important, and so most of the variables could be explained with that. And now we say, okay, within these reduced subset, we can optimize with the help of this meta model, because this meta model is only a mathematical function, so it can be solved very, very fast.
Excuse me if to interrupt you. I guess your screen is stuck. I'm at the optimization slide.
Yeah, yeah. But it's the optimization slide, and since it, maybe the red dot is moving?
Yes.
Yes. Okay.
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 I'm sorry.
No problem. Yeah. Yes. So we want to find the parameter set which is increasing the performance of our filter system. And now, yeah, you will get these slides to go through this theory. I will skip these for now. Only the remark. Of course, you need an objective function. This is the parameter which should be minimized or maximized. And you can as well have a lot of these objective functions. So we will start in that example here with 4 objectives, and then we will reduce them to a single objective optimization. And you can as well use constraints to describe, yeah, the restrictions you have to take care of within your, yeah, response space. And optiSLang provides you with a few optimizers, gradient-based, adaptive response surface methods, and nature-inspired optimization methods. And the workflow will look like that. First of all, we have done sensitivity analysis to identify the important parameters and to create the surrogate model, which will be used as a replacement for the solver call within the next step. So we will start with the optimizer, and the optimizer will try to find or a suggestion for a good parameter set, and then we have to validate this final design which the optimizers have found on the surrogate model. And then when we have validated this design, we can decide if we want to do a second optimization here with the solver runs, or do we find these found design good enough. So here you can see again, optiSLang is using these traffic lights to showing the suitable optimization method. And for these traffic lights, the number of input parameters, the analysis status, and solver noise, and a few other things are used to calculate that. And how would it look like when we set up such an optimization? We take the optimization wizard and drag it on the surrogate model. Now in this case, we should adjust the parameters a little bit. So when we have done that, we can go on into the criteria definition. These will be imported again from a file. And you see we have different objectives. Like I said, these are 4 objectives. One for the efficiency, which should be maximized, and one for the initial pressure drop, last pressure drop, and the deposited dust. And we thought, okay, as well, we should include 2 constraints here to find only designs which have a minimum efficiency and a minimum deposited dust. So when we have defined that, we go on. The traffic light is indicating, okay, we should stick with the evolutionary algorithm, and we will do that. And here we can go on. And now we would solve these optimization task on the surrogate model. I would like to present you these results immediately, so I change the project. And here we found the Pareto plot for the optimization. So the Pareto plot is describing the conflict between different objectives we have. So in this step here, we show 2 objectives, the efficiency and the initial pressure drop. And you can see there is a slightly conflict between them. So when you want to increase the pressure drop, increase the efficiency. The pressure drop is increasing as well, but we want to go to this point, to a low pressure drop and a high efficiency. So you see this point cannot be reached. And as well, we can check the efficiency and the last pressure drop. And here you see the same behavior as well. And the dust is quite similar in the behavior. So maybe we should check the initial pressure drop and the last pressure drop, for example. And here we will see that these objectives are not in conflict. So the only conflicting objective is at the end the efficiency with the pressure drops. So we can decide how to go on here. And that's what we have done as well within the slides. So we can decide that these 4 objectives are quite suitable, but we can reduce 3 of them. And why should we reduce these objectives? Because we want to achieve one single best design, and only one single best design is possible if we are using a single objective optimization. So, and in the suggested workflow, you would use the multi-objective optimization like we have shown already. Then you can go on and weighting the objectives, or you can reduce the number of objectives and replace them with constraints. And then you can make the single objective optimization, and then you can validate these best design. So in this case, we have decided to only use the final pressure drop as optimization objective. So when we again look here, you will see that the final pressure drop is the objective, and the other one, the initial, for example, here has a constraint which is limiting these value to 60 Pascal. And with that, we can again have a look here. So you will see that we are limiting these possible range of results from 60 to 99%. So this range is possible, is suitable for the application. And then we can, with this knowledge we have found here, we can go on and can decide, okay, we should make an optimization with the NMPQL. So we can import these parameters now from the evolutionary algorithm. Then we will import the parameters from a file again. And so here you can see again these 3 constraints we have used and the 1 objective. And now the NMPQL as gradient-based method is suggested. So we want to stick with that, and we want to validate the design at the end. So this is how this project would look like, and we want to see the results immediately, I assume. So we should go back to a project which is already calculated, and here we can see the post-processing for a single objective optimization, and you directly see here that 2 points are shown for this design 121. So this design 121 is the best design, and this best design was validated automatically. And then we can check the differences between the calculated best design on the surrogate, on this meta model of optimal prognosis, and the best design values from the GeoDict simulation. And you can see that this surrogate model is only an approximation, so there is a slightly difference between these values. But for our application here, this difference was good enough, and so we can or could choose to stay with these values. when we stay with these values, we can compare these optimized and the original simulation result, and we see that within these 51 simulations we needed. So we needed 50 for the sensitivity study and 1 design for the validation, that we achieved to improve the design. And now we could go on and use this design within a CFD simulation or within another simulation. So now it's your part to ask us a lot of questions. So here you can find the contact information for Dynado and Map to Market. And now we would be glad to hear your questions. So if you are too shy to ask your question within this webinar, you can of course write us an email to ask your questions, and then we will answer them as together.
And for your information, the release of this integration will be with the next release from optiSLang.
This release was last week.
Oh, okay.
Yeah. Okay. So thanks a lot for your participation. Feel free to get in touch with.
Thank you a lot.
Yeah. Okay. Yeah. Thank you, Aaron, for your presentation and for your time to prepare this example. And so, if anybody has any questions later on, so feel free to get in touch with us. So, bye and have a nice day.
Bye and have a nice day too.